CLI and a cross-platform IDE for C and C++. Download now.
Hi, I'm Daisy Hollman. Many of you know me, but I am now working at Anthropic. Who here has not heard of Anthropic? Oh, I wish I had a shot of this room that I could send to my bosses to get to talk more. Who here has not heard of OpenAI? For the record, 0 hands. It was about half the room. They are our closest competitor, and we are actually beating them on coding benchmarks by a lot. So Anthropic, we make Claude. We only do AI. We only do large language models. We don't do any of this image generation nonsense. But although our code generation has gotten to be so good that it can write raw SVGs pretty well that make images, and all of the diagrams in this talk were generated by Claude. All of the styling for this talk is JavaScript in reveal.js, written by Claude. I recently started at the company 6 weeks and 2 days ago today, which is amazing to me because it feels like I've been there for 6 months, 9 months. Time moves very slowly in AI, very slowly, very quickly. Everything moves very quickly. But before I was at Anthropic, I was at Google for 3.5 years. I was at Sandia National Labs in the US for 7 years before that. At one point, I was a quantum chemist. That's what my PhD says anyway. I don't know that I was ever really a very good quantum chemist. I've been involved in the C++ committee for more than 8 years now, although I am taking a little bit of a step back from that to work on Rust. I did IndySpan, I worked on executors, I worked on atomic ref, ranges, all the easy stuff. That was a joke. AI has been a pretty small part of my career so far. And so I am like you all, I had pretty little experience going into a company that only does AI. I was pretty convinced by their mission and their focus on AI safety and bettering the world through AI. And that's why I was attracted to the company. And somehow I convinced them to hire me, even though I have very little experience in AI. They hired me to do programming languages work. So I have some experience with that, but anyway, so I, like 6 weeks ago, I was like most of you, just kind of not knew that it was kind of a thing that was happening to our industry. So I'm going to try and summarize the things that I've learned over the past 6 weeks as I've kind of gone through this whirlwind adventure in AI. And I'm really excited. Anastasia did a fantastic job setting up my talk. And there's a lot to talk about here. Okay, so we're going to talk about how LLMs work. I'm going to go in a little bit more detail. We'll talk about both inference and training. Agents is the hottest thing in AI right now, and I'm going to talk, most of my talk is about agents. I think that's the thing that's mostly worth talking about in AI right now. I think that's the direction everything is going, and your kind of standard prompt response loop is chatbots are just kind of the first thing that we happen to do with LLMs. They're not going to last. Or they'll last, but they're not going to be the main thing. Coding with LLMs, we'll talk about what they're good at. We'll talk about some best practices, which, spoiler alert, they're just best practices for coding with humans. And we'll talk about what they're bad at so far, which will probably be irrelevant by the time this goes up on YouTube because, I don't know how fast it'll go up on YouTube. It's a keynote, but it'll be irrelevant in 3-6 months. So this is April of 2025 for anyone watching this in the future and laughing at how primitive all of this is. And we'll talk about the thing that I really, really want to talk about, which is why I always put at the end of the talk so that I actually get through the talk, which is evolving programming languages in the AI world. I think I have some interesting insights here, and I want to kind of geek out about it. So let's hang out and let's chat. We'll start with what is AI and what do I mean by AI. XKCD quite a while ago said that AI is this like pile of linear algebra that you pour data into and collect answers on the other side. And if the answers are wrong, you just keep stirring it. It's like all XKCDs, it's scarily accurate. But the funny thing about this XKCD is that I am not great at adding jokes to my talks, or at least adding jokes to my slides. I guess I do add jokes to my talks, but I'm not great at adding jokes to my slides. And so I asked Claude to look at my slides and suggest a good joke to start out with, and it suggested XKCD number 1838 would be a good way to start off this talk. And you can go read this later. The slides are all, by the way, at this URL over here, daisyh.dev/talks/accu-2025. And they're live there right now. Okay, so let's talk about large language models. In this talk, I'm going to use the term LLM and AI interchangeably. Is this going to work, or is this a really bad idea? The problem is I am wearing a dress and I don't want to bend over to get my water, but I'll make it work. Okay, so large language model, AI, I'm going to use them interchangeably. There's a lot more to AI than large language models. Image generation, for instance, is a thing called diffusion, which is a completely different process from large language models. But we're going to talk just about large language models, mostly because they're the most relevant to code. This is the thing that you need to know about if you care about software engineering. We are mostly going to talk about frontier models. And this is going to sound really self-serving, but I promise you this is the general view of the whole industry. There are basically 3 frontier models and then a couple of others that are kind of sometimes thrown into the mix. And by frontier, I mean the models that are leading at all of the benchmarks. And the benchmarks have gotten to be crazy complicated. One of the most prominent benchmarks is called SWE-bench. And I think it's basically a bunch of GitHub repositories and issues pulled from those GitHub repositories. And that's all you give it as input. And it has to pass all the tests by the end. Like, it's that kind of thing. And so these are real problems. They're not necessarily just benchmarks. And so the 3 models that are consistently leading at one benchmark or another are OpenAI's models, generally called ChatGPT, but they're not very good at naming them. So they name them like O3 Mini or O1 or 4.0. And Anthropic's Claude and Google's Gemini. Those are the 3 that are kind of jockeying for things. There's a few other models, Llama and DeepSeek. Grok is probably from Llama. We don't know that for a fact, but and DeepSeek is probably distilled from larger models. We don't know that for a fact. That's for courts to decide. But another discussion there. DeepSeek did introduce some interesting things that I'm going to talk about, but for the most part, it's this kind of subset of models. There's a lot of other interesting things going on in the AI space. There's a lot going on in green AI that's actually really good research that needs to be done. There's lots of other things, but I don't have time to talk about everything that's going on in AI, so I'm focusing in on frontier large language models for now. And frontier also means pretty much anything that didn't come out in the last 2 months is pretty irrelevant at this point, which is crazy. And I won't even say 2 months because, like, when did Claude 3.7 came out beginning of March or end of February, and then Gemini 2.5 just came out, and ChatGPT 4.5 just came out. Those are the 3 relevant models. Everything else is irrelevant at this point. And those are all within a month. So that's how fast this industry moves. Anything that happened in January is somewhat irrelevant. Which is blowing my mind. So let's talk about this. I've heard this a few times. LLMs are just predicting the next word. And that's like mechanically true, but it is the most misleading thing you could say about them. It's like saying a chess engine is just predicting the next move. Like, mechanically, the output of the chess engine is the next move. But to say that all it's thinking about is the next move, or to say it's not thinking, it's just throwing out the next move, and then once it has the next move, it throws out the next move. That's a pretty misleading description of a chess engine, I think you'd agree. And it'd be pretty hard to beat a human playing chess if that's all you were doing, right? There's a lot of thinking and reasoning and taking into account a lot of things going on when you are predicting the next word. Speaking of which, let's talk about AI skepticism. There is a lot of hyperbole in AI rhetoric today. Some of you may have thought that what I have said so far has been hyperbole, and there's a healthy amount of skepticism. Good. It is fantastic to be skeptical of new changes in this industry. There is a lot of hype. There is a lot of money being thrown into these things. And it is not necessarily good to believe everything you say. But the opposite of that is I wouldn't stake my career on it being wrong. I think there are a lot of people who are saying, now wait a couple years and see what happens. A couple years will be too late, right? If the AI hype is correct, then you will be way too far behind at that point. So definitely this is something to stay on top of. Definitely, I think there is a very good chance this will fundamentally change our industry. And it's something, and I'm not just saying this because I'm at an AI company. This title for this talk was in my brain before I even applied for Anthropic. So it's been a whirlwind thing. I applied to work there in like January and was started February 18th. Like that's, I don't know how all of that happened. I'm certainly glad it did. It's been an amazing thing. At the end of the day, it's a tool. And this industry runs on people efficiently using tools. It is true that LLMs are much better at augmenting engineers than they are at replacing us. They are good at boring mechanical tasks. I am going to try and convince you that the things that it is good at are things you will not miss. And you will still get to do the interesting parts of software engineering, at least for the foreseeable future. All right, let's talk about the bitter lesson really briefly. Anyone in here know what I mean when I say the bitter lesson? It's a very famous AI blog post. Wow, I was not aware of how disconnected these communities are. I have so much imposter syndrome at Anthropic because it's just in the water there, and everyone, oh, the bitter lesson. I heard it probably 3 times in the first 5 days I was there. It's the Moore's law of AI to some extent. It's the thing that people reference in a lot of different contexts. It's this observation in 2019 that general methods leveraging computing consistently outperform specialized approaches. In other words, as Claude told me to meme, we could, yes, this. And we've seen this over and over and over again in image generation, language translation, computer vision, speech recognition. LLMs follow this pattern. AlphaGo versus AlphaGo Zero, if you followed that saga at all, is exactly as an example of this pattern. Image generation, just recently, there's I don't know if you remember when we first saw image generation, they were having a lot of trouble with the number of fingers on people's hands or on the pictures, the hands in the picture, right? Or they were having a lot of trouble with text, right? The text was always like some approximation of what a letter should look like, but didn't mean anything. And I mean, so several companies, startups were founded on going off and like hyper training these image generation things on text specifically. Like our model is the best at generating your image if it has text in it. And then the most recent general models just came out this month. And they've all caught up. They can all do text. They all get the right number of fingers pretty much every time. It's like the general version eventually outperforms the specialized version. Yeah, decades of AI history have shown this. And the bitter part here is humbling for us, right? Because it's human expertise in the domain is less valuable than we thought, which really sucks. It really, really sucks, doesn't it? Like, but this is why this gets referenced so much in AI. All right, here's my attempt to go over how LLMs actually work. I am not an expert in AI. I am not an expert in neural networks. I understand a little bit of the math, or the math from 7 years ago or something like that. But I have had actual AI experts look at this, people who have PhDs in machine learning, and they have said it is good enough for what I'm trying to get across. There are lots of things in here that are oversimplifications by a lot, but it gets across. The point here is this is my working model that has really helped me improve as a software engineer. And it is accurate enough to draw many of the correct conclusions. Okay, this is a picture Claude drew with an SVG, just from a prompt. Actually, I think the prompt was explain LLM architecture to me in a picture. Like it wasn't. And then I showed it to an expert and it's like, yeah, that's pretty good actually. And there were a few little tweaks and I made the tweaks, or I told it to make the tweaks. But we're going to talk about this in 3 different parts. The first part is the embedding layer and tokenization. This is the layer that turns words or tokens into vectors, right? Tokens can include words. In some cases, they're going to be single characters if it doesn't know the word. In some cases, it's going to be a space or punctuation. There are a number of other things that get used as tokens, and tokenization is a field that's evolving. And tokenization for code specifically is a field that's evolving pretty rapidly. There is a limit to the number of input tokens that the model can be trained on, right? We are doing dense linear algebra on these things. And so you have a very fixed size that the training happens on. I could go into the math on that. I don't have time. But there is the fundamental takeaway here that's most important is that there is a fixed context window, which is basically the number of tokens that an LLM can think about. This is if you don't get anything from the next 10 slides, remember this one. This is the most important thing to take away here, because basically everything built on top of LLMs that's not from one of those 3 companies is something that is trying to take best advantage of this context window, right? It's called prompt engineering is the term that people use. And I hate it when people say prompt engineering isn't engineering, because that's an elitist approach to this. It is a real skill and there's a lot to it. And a lot of products are being made off of that. And for the context of software engineering, I think the most important thing to understand is ways to efficiently use this, right? That's the part that you have control over. Let's talk about transformers. Transformers are the miracle that made the LLM revolution happen. I am realizing after my first 2 questions for the room that this joke is not going to land on the first side, and seeing no teenage girls in the audience, it's not going to land on the second side. So this is going to be fun, but who knows what goes in this blank? Hey, we have 2 people. Attention. Yeah, Charlie Puth predicted it 2 months early. That was the teenage girls part, and there are none in the audience. So fantastic song, by the way. You should look it up. Transformers build connections between related tokens that may be far away from each other in the input, right? So this is what basically the idea is. That's what these orange lines are. That's what Claude was trying to illustrate with these orange lines. But I asked Claude to do a better job of illustrating it, and it came up with this. Basically, the idea is you have this matrix that says, how connected is this word to this word, right? This is a way oversimplification of how attention works. And there's all kinds of interesting things. There's something called self-attention also that does something different. And there's lots of tweaks to this. There's ways to take advantage of sparsity in this matrix. It's a method called LoRa, low rank approximation. But the main point here is that if you have a sentence with an intervening clause, or a paragraph, or you have a preposition in a future sentence, and it's obvious to humans that preposition refers back to something in a previous sentence, attention allows the LLM to build those connections, right? So it builds this strong connection between student and past in this long sentence that has an intervening clause. That was kind of very early on when attention windows were very small, or attention, and now we are doing full attention on 200,000 input tokens and things like that. And so it can, in theory, form a connection between the very first token and the very last token in the window, and still know what it is. But there's a lot going on there, right? And there's a lot we don't understand. We are still doing the stirring of the data until we get the right thing out, right? The XKCD is scarily accurate. All right, outputs. The model is a probability distribution. The output of the model is a probability distribution of the next token. So this is why I preempted this with saying it's just predicting the next token, because mechanically it is just predicting the next token. It's giving you a probability distribution. You're going to take a sample from that. It's called sampling. Use a function called softmax usually. There's lots of versions of that, lots of variations of that, but usually there is a temperature parameter that controls how random the sampling is. Low temperature, close to 0 is more deterministic. If you do actual 0, it's just pick the most likely token every time. And higher temperature can lead to more creativity and more randomness. We're still trying to really understand the effects of temperature on these things. And you sometimes want to vary the temperature depending on the application, even sometimes depending on the part of the output, right? Like maybe if you're composing a JSON file that needs to have quite a lot of hard structure to it, then you'll turn the temperature down for a little bit and then turn it back up. You have this parameter that you can do, right? And then you add that one output token to that window and repeat the entire process. And there are hundreds or thousands of these layers. There are hundreds of these nodes in here. And these are enormous computations, right? Like orders of magnitude larger than things humanity had done before this. And yes, the carbon footprint is something absolutely that we should be thinking about here. It is lower for large language models than it is for image generation, but it's something that a lot of people are thinking very seriously, and I'm very proud to say a lot of people at my company are thinking very seriously about and taking action on, putting money into. So, man, that's a big reason why I'm at Anthropic. I'm a big fan. This is not an advertisement. It's just a fact that I'm so happy to be there. Anyway, let's talk about the context window, right? I said that's the most important thing to remember, right? How does a LLM remember previous prompts over the course of a long conversation, right? Like, let's just go back to the chatbot version. How is it incorporating your previous prompt and then its answer and then your next prompt? Because you can say like, how does it work? And it can refer to something in their answer. It's shockingly primitive. We're putting these special tokens. They're not even special. Sometimes they're just literally the words. I think eventually they're going to have to be actually special because it's too easy to confuse it by sticking the words in yourself. But it'll use, in this case, at Anthropic, we use human and we use assistant with a colon. And we separate the prompt from the response. And that is like, I put this example up because pretty early on at Anthropic, I had a situation where I was building something as a proof of concept, and the test ended up, the proof of concept output ended up with one large language model talking to another one. And I told the first one to like test that the second one was working, and it immediately started talking to the second one about Pokemon. So I copied this conversation from that particular test, and I think it's hilarious. But like literally, this is what you're stuffing in to the context window. And if you are trying to predict this word, then this whole thing is your context window, right? If that's the token you're trying to predict. And you can see the effects of attention here right away, right? You can see that when it says, what is water weak to? It knows that water and Pokemon are connected. Because otherwise, like, what is water weak to is a pretty nonsense question. And you'd be like, evaporation? I don't know, right? And then here I say, does it have any resistances, right? And it's able to in one layer, make the connection between it and water while still maintaining this connection in another layer between water and Pokemon, right? And so it's like, oh, I know you are talking, not only does this it talk about water, but this water talks about Pokemon, right? And so this picture of how attention works is actually pretty useful for thinking about how they're going to reason about code. Your brain starts working on that picture. It's actually quite useful. It's been very helpful for me, and I've been able to use LLMs quite effectively through this. But there is a whole lot of hand waving, and long conversations use a lot of tokens really quickly, right? If you have 30 prompt response loops, right? On your 31st prompt, you're using all of the tokens from the first 30 prompts. And that's, there's some caching tricks we can do. We can certain parts of the process that I'm not gonna get into math-wise, can be cached. Other parts cannot because they get recomputed every time. But it is effectively as expensive as it sounds. All right. So let's talk briefly about training LLMs, and then we'll dive into the meat of the talk. Training of LLMs is complicated, and it's this big art. And there's this first part that you're really just predicting the next token with. And then there's this second part, which is actually improving on that. And the first thing we do is we literally crawl the whole internet. I'm going to say this a bunch of times. LLMs ran out of data a long time ago. 2 years ago, this became insufficient amounts of data. The entire internet is way too small, which is hilarious to say, but realistically, this is true. For random data sets that don't have any kind of refinements to them or pick out the really good parts, the whole internet is way too small. Yeah, so generally our largest source of data comes from scraping the internet. We also legally purchase rights to use books. We purchase rights to use academic papers, images, a number of other sources. There's a lot of really creative things. One that I asked for permission to talk about and never got an answer, so I'm not going to talk about, but there's some really interesting and creative things that Anthropic is doing to get data sources legally, legitimately. There is a lot of really well-meaning legal insight going into this. I'm not going to talk about it because I am not a lawyer. I understand that there are a lot of concerns here too, and I get it. I have seen LLMs quoting my cute C++ tricks before, and I'm like, I don't know how I feel about that. And so, yeah, this happens. Frontier models started running out of data a long time ago, and we've got a lot more creative about how to get data, how to refine this data. Pre-training is really the process of training on this kind of widespread read the whole internet data, right? That's what used to be LLMs 2 years ago, which is an eternity ago. When did ChatGPT come out? Late 2022? So 2.5 years ago? 3 years ago? No, that's 2 years ago. Wow. Yeah. So that was called training back then. And now we call that pre-training. And you start with random values for all the weights or variables in the model. In a very, very, very oversimplified sense, you kind of perturb the weights and see what happens, right? And if the perturbed weights are better at predicting the next token based on that whole data set, then you keep them. And if not, then you kind of take a step in the other direction. It's more complicated than that. You take a gradient mathematically, and then you follow that gradient. And actually, gradient descent is very much a lie right now because that's way too primitive. We do things that are much more complicated than gradient descent at this point. But yeah, and then you repeat until the weights kind of stop changing within some tolerance, right? And then is when the real training starts. So we do reinforcement learning, where you give the model a task and a reward signal, right? And if make the tests in this code base pass, right? There is a definite art to this. There is a lot of trade secret to this. So I'm not going to get a lot into detail, and I don't know a lot of it because it's trade secret and I don't have need to know. Um, but supervised fine tuning, reinforcement learning with human feedback are two of the acronyms you'll hear in this space, SFT and RLHF. And there are quite a lot of subsets of that that go on. But in the context of software engineering, it's very often things like this. It's make the tests in this code base pass, or update this code to do something different, or things like that, right? And you give it that task, and then you run it on that task, see how it does, and perturb the weights, and then see if it does better. And if it does better, keep the new weights. And again, there's gradient descent involved, and the methods in math are very difficult. But like conceptually, that's what's happening. You're kind of randomly walking through this multi-billion dimensional space and seeing if you land on something that's a little bit better than what you had before. And yeah, you repeat for many different versions of task and reward in many different domains. There's more going on there. There's this thing called mixture of experts, MOE, that you'll probably see around, that's become very popular lately, that improves on this a little bit. You're not necessarily mixing all of the experts into one reinforcement learning run. There's a lot going on. But I think that overview should be sufficient for what you need to know for software engineering. Let's talk about agents. Agents, this is the really big hot thing in the past, really 6 months, but especially the past month or two, that really the latest set of models has gotten to be strong enough to really, really efficiently use agents. You've probably seen quite a lot of these things on YouTube, et cetera, where people will put a single question in and you'll get an entire like well-researched, well-cited paper out. That's an agent going out and iteratively reading the internet, reading something more, doing a web search based on something it read in one paper and following up on that fact in another paper. It can do this for code also, but these are not acting on this simple prompt response loop, right? It is going out, you're giving it a goal and it's breaking it up into a bunch of different tasks. And I'm getting ahead of myself on my slides, so let's wait till we get there before I get too excited about it. But I really do think agents are the future of large language models, and I've been keeping an eye on this for a while, even before I was at Anthropic. And when you join a company that's working on something this new, you go from like seeing what the public is seeing to living 3 months in the future. And I was like, holy crap, because 3 months is a very long time in AI. And this is fundamentally going to change the way that the world works in many, many industries. I think software engineering foremost among all of them, because everything we do is text, right? Like, does anyone regularly do in their day job something that doesn't boil down to text? Yeah, right. Like, all we do in this industry is text. And there's very few industries that you can say that about, right? But main key characteristics of agents, besides this whole multi-step thing, they are starting to get much better at tool use, which I'll talk about in a later slide. Planning and reasoning, they create a plan and then they break it into smaller tasks, and they do those tasks in an iterative way, or sometimes even in a parallel way. Decision making, feedback-driven self-improvement. It can go run the tests, and then when the tests pass, it can say, okay, or if compilation fails, it can go fix compilation errors, those kinds of things. And goal-directed behavior is another characteristic that people say. But agents are still limited by this context window, right? Like, everything the agent does is being stuffed into this context window. Now, you can play around with that. You can have like sub-agent tools where the agent will go and say, I need a summary of this big, long document. So I'm not going to load the whole document into my context window. I'm going to load the summary, and I'm going to go get another agent to go read the thing and summarize it to me, giving me the important points with respect to this piece of information, that I'm trying to work on. But in general, you're still trying to find cute ways or interesting ways to use this context window efficiently. And so it still all boils down to, in our models right now, it's 200,000 tokens. In Gemini's model, it's 1 million tokens. There's anywhere in between. There are advantages and disadvantages to larger context windows. It does seem like we're getting a little bit diminishing returns on larger context windows because to some extent training the attention at that scale is too expensive, and sometimes you have to start making sparsity assumptions with the training of the larger context windows, and then you lose something from that. And so there's a lot of discourse about how to maximize context windows, but I don't think they're going to grow arbitrarily. Like, it's hard to say anything in this industry right now, but like 1 to 10 million tokens maybe seems like probably the limit of what we're going to train with full attention. 200,000 is pretty reasonable right now. So let's talk about tool use. So, I mean, keep that in mind as we're talking about all of this. Everything that's happening is getting stuffed into this one context window, right? And that's really important for thinking about how software engineering is going to work. So let's talk about tool use. At some point, researchers were like, oh, hey, JSON, that's text, right? Like, I can just have the LLM generate JSON and then pass that to like a normal traditional computer program and have it do something. And so that's what we did. We started giving it a JSON format and some examples as part of this context window. So it still has to be in the context window for the LLM to be able to do it, right? It's not in the weights or anything like that. And said, here's how you would control this tool. If the user says they want to do something related to that, produce this JSON to control this tool, and you'll get this type of output. Like, we put those kinds of statements in there. It's prompt engineering. And we can put anything we want on the other side of the tool. Most often it's a terminal. A terminal in software engineering most often is terminal, but code repositories, databases, it can run and compile and run the code, which is critical for self-improvement, right? It can search the internet for information about something, right? Like, you want to be careful with this because you don't want to leak information about your proprietary code base to the web. And so maybe you do want to turn web search off for when it's working on this part of the code in case something ends up out there. But you can put restrictions on these things. You can be very careful with these things. You can tell it what files to touch, and you can give it subsets of these tools. But fundamentally, this is how it's interacting with your code. And this is going to be really important to understand as we start talking about how we can improve software engineering and our habits to adjust to this future, if it does come to be. Another interesting tool, which I'm going to talk about here, is the code search tool. And it is addressing this interesting question. How do agents understand 1 million plus line code bases with just a few 100,000 tokens of context? Now, if the fact that I'm saying agents understand 100 million plus line code bases is a surprise to you, which I, coming into this talk, didn't think it would be, but it might be, because I guess you're not drinking Anthropic water all the time. I mean, this is 3 months old news that, like, oh yeah, we have these agents that are starting to be able to understand 1 million line code bases, and like really give real insights into it. The better question to ask here that actually will give you a lot of the information is, how do humans do this, right? There's not a person in this room. There are Clang developers in this room. There's not a person in this room that can recite every token of Clang, right? Like, that's hilarious, right? And to think that that's the way we should go about it with LLMs is silly, right? We search through the code, find a key entry point, like the simplest one being main, but there might be other entry points that are interesting, or there might be a function that you grep for if you're looking for a particular type of function. And then we read the code in those entry points, and maybe like if there's one or two of the functions that were like seem really important and we want to know more about it because that would give us a much better understanding of the behavior, we look at that. Whereas if there's a function that we're like pretty much can guess what it does, and we're like, okay, yeah, I don't think there's anything interesting in there, we just kind of keep in our mental model that that function is doing something. And then if we later find out that the program is doing something weird, we might go back and look at that function because, like, maybe that's not doing what I thought it was, right? Like, all of this kind of behavior, you'll just analyze what your brain is doing. Whoops, that is the end of my presentation. What happened? All right, let's go back. Sorry, spoiler. What? The agent processed it. And so, yeah, if we want to understand a specific piece of functionality, we search for key strings and patterns, and then we look at the code around those strings, right? In other words, we're like loading pieces of that code into our context window, right? And we might load summaries of other pieces, right? We might go say, like if we've been working on it for a few weeks, we talk to people who work on the code base and be like, oh, how does the AST work in Clang? I'm working on the semantic part of Clang. And I just need a kind of a conceptual overview. And sometimes agents will go send out other agents to get a conceptual overview of a different part of the code and get a summary back. And they'll kind of decide which parts they need a summary for and which parts they need the literal code for. And this is being iteratively refined as we speak. And the problems people are saying, oh, is AI plateauing? And the problems you'll see, I'm going to talk about a few of them. The problems in this space and the solutions in this space are surprisingly primitive. They all feel like low-hanging fruit. It feels like we are still in the phase we are picking the low-hanging fruit in AI. And that's what scares me. That's the thing that keeps blowing my mind inside of Anthropic, is seeing the things that people are doing that feel like low-hanging fruit from an engineering perspective. And so I think this is really, like, my estimate is this is going to change the world in ways that we can't even see yet. Yeah, and agents do this. This is the point, is this is exactly the process that agents use to understand large pieces of code, and I have a video. So it's not a demo because agents work very quickly. They cannot understand Clang in a 5-minute demo. And you'll see the time ticking up. But yeah, let me first talk about, so we have this phrase inside Anthropic called your red pill moment. When was it that you decided to go down the rabbit hole, right? When was it that you decided that it was worth dedicating at least the next few years of your life to this? And I had a few, I was pretty convinced that this was something that was interesting to work on before I got there. But the real crazy thing for me was my second day at Anthropic, my third day at Anthropic. I'd done 2 days of general onboarding in an onboarding class that was, salespeople and technical people. And there was nothing really all that technical in the first 2 days. I get to the third day and I'm like, I kind of want to start doing something real. Take a look at the Anthropic monorepo. It's about 500,000 lines right now. And it's mostly written in languages I haven't worked in the past professionally. I'm a languages person, so I'm kind of comfortable in a lot of things, but I haven't done professional work in Python in a while. I haven't done professional work in Rust ever. I haven't done professional work in TypeScript for all of our front-end stuff ever. This is my third day at Anthropic. I've finally gotten my list of startup tasks, and I can't put the actual words in here, but it's literally make feature I haven't heard of, faster using tool I haven't heard of, or maybe other tool I haven't heard of. That's how my brain processed that sentence, right? And, oh yeah, this will change every production image we build. And if you get it wrong, we'll stop running in production. Not kidding. I wish I were. Working at a startup is wild. If you've never done it, you should try it at least once in your life. And my colleague on my team, I'm not saying that it's always good, don't get me wrong, but it is a wild experience. And my colleague is like, hey, I'm out this afternoon for a dentist appointment or something. I'll give you a tour of the code base tomorrow morning and we can dive into this. And so I had 3 hours in the afternoon, wasn't really ready to go home or anything like that. And so I was like, I wonder if Claude knows how to do this. This agentic tool that I'm going to be showing you in this talk had just launched internally the week before. And we were still trying to figure out, I was the first class to be onboarded with this 6 weeks ago. And now this is all over the place. Every major model has something like this. And so I kind of dove in and started playing around with the tool. And I said, what if I just copy this and say something like, I'm new to this code base. I don't really know what I'm doing. Can you look around and tell me where I'd even start on this and what I would try and do? We had a little bit of a conversation about it. It kind of dug in. And 3 hours later, the pull request was ready. I literally did not change that pull request from Thursday afternoon. The next morning, my colleague walks in and says, oh, I see you sent me a pull request before I gave you a tour of the code base. How did that happen? And I said, this is the future we're living in. This is onboarding costs and onboarding times are going to go to zero, right? You are going to go from 0 to 6 months of the company in a few days. I think that is going to be the reality of even a very large company with a very large code base. Like 500,000 lines is not Google's code base. I get that. But it is very large. And it is like, I have worked on it with larger code bases. Let's look at an example of this in the context of Clang. Clang is 1.4 million lines of source code, roughly, if you count all the table gen stuff, which is definitely should count because that's not anywhere else. And so it's got to figure out how table gen works, right? Alongside figuring out how all the C++ and Clang works. And so this is me running Claude in the terminal. It has done nothing. I haven't given it anything. It starts its context with a system prompt. And the first thing you do is when you're on a code base, you type /init, and it will go through and kind of get an overview of how to interact with the code base and create its own claude.md file, which is basically like, hey, it's like the robots.txt of a Git repository, right? It's like, here's how you interact with this repository if you are an AI agent. Naming it claude.md for our particular case is a little self-serving, but whatever. Maybe there will be an industry standard name for it at some point. But this is where we kind of go through and figure out how you interact. It'll go through figure out how to build the thing, right? That's one of the things that it does is it goes and figures out how to configure the build system and compile it so that it can run tests, right? Those are all very essential things. And the idea is that you don't want to have to do that every single time you start the tool, right? And so now I'm going to give it a question, like a real question, to try and understand the code base. And if you've ever worked in Clang, who in here has edited Clang before? Who here has had an accepted pull request? One person. Woohoo! I'm not raising my hand. I have edited Clang. You can see actually the videos of me trying to get up to speed on it. They're all on Twitch. I live stream myself doing it. I got up to speed to the point at which this thing is going to get to, which I'll show you in a second. It took me maybe 20, 25 hours, and I had someone in my Twitch chat who is a regular Clang developer guiding me the entire time, right? Yeah, anyway, let's do this. So I'm like, hey, I'm interested in this feature, const per if, which is named, oh, I didn't stop it soon enough. It's named if const expr, and it's like, I want to know how it's implemented in Clang, right? Like that's a thing that a C++ nerd might want to know, right? Like, just for curiosity. And I say, walk me through how Clang handles it. Show me key line numbers and files where I can learn what's going on, and explain what each other does. This think harder is it's funnier than it sounds. It's our current hack on Claude Code. This is Claude Code, by the way. It's our agentic tool that we're putting out into the world right now. But right now we don't have a UI-based way to turn on deep thinking or extended thinking windows. Which, if you don't know what an extended thinking window is, I'll explain it later in the talk. It's hilarious. Not hilarious. It's actually brilliant, but also hilarious how simple it is. You'll agree with me when I say low-hanging fruit. But the way that we now turn on extended thinking in Claude Code is that we grep the prompt for the phrase think harder. And so you'll see me putting think harder into some of these things because for a code base like Clang, it's absolutely essential. It's just way too complicated for it to do immediate prompt and response. It has to do some extended thinking in between. And so I go, and you will see why I didn't do this as a live demo. Look at this is seconds. This is counting up. I am speeding this up substantially. It is taking a while. It is taking a very short time compared to most humans. But it is taking a while, right? And so it actually goes into the AST, and it found the important part of the AST. I actually haven't checked if this is a comment that's in the code base or if it's actually added the comment itself. I suspect Clang is pretty good at having informative comments in places like this, so maybe it just found this by gripping. But get non-discarded case. So this is how you pull out of the AST the block that is not discarded in a const per if. And then it shows me the implementation of get non-discarded case. It gets it a little wrong. It doesn't really understand what value dependent means here, that it has to do with template instantiation and stuff, which I don't blame it. Tree transform, if you've ever read it in Clang, is a bit of a nightmare. It's brilliant and it works really well, but it is a bit of a nightmare. But it walks through that code. It gets a little bit sidetracked by code generation, and actually off of this video, I asked it, well, how, like, probably trying to emulate the question that someone reading through this and getting confused would ask, is that, like, how come we're talking about code generation for const_exp if the block's already discarded? And it came back and said, oh, I may have mixed up constant folding and constant expressions, which constant folding is the thing that code generation does, right? And yeah, I mean, like, it's going to get some things wrong at the start, but not all of them, right? And it goes through here. Let's see what else it has. It talks about the handling of unused branches. And so here's the interesting thing, right? I say, if I want to implement switch const_exp, I don't even give it, like, I say it extends it extends this sort of functionality. So you can see the role of attention there, right? This sort of functionality, it's referring back to all of this information that it's now learned about what if const_exp is. Because coming into this, it did not know anything more than what was in its pre-training data from the internet about if const_exp. It knows something from its pre-training data, but not a lot, right? I said, create a thorough project plan with instructions and descriptions of everything that needs to be implemented on a scale of 1 to 10. Estimate which of these tasks are easy and which of these are difficult for you to do and would require a human, right? And I said, think harder. I cut out a lot of the thinking. This was 20 minutes-ish. I actually paused the recording and came back because it was so long. These are really intensive tasks. We are getting a lot faster at these things. And things that I can't show you are faster by amounts that I can't show you. But the reality is that you are doing human scale computations, and human scale computations, humans are slow. And we've always been like, oh, but computers are fast. And that's because computers are doing things fundamentally way less complicated than we are. And now that we're starting to do things that are as complicated as what humans do, we're like, oh, computers are kind of slow. And we're like, no, actually, humans have always just been really, really fast. Yeah. And so it goes through and it says, I love this part. It gives 8, 9, and 7 to writing the language proposal and getting it approved. Which is interesting. The interesting part about this that I actually think is pretty accurate is it says defining the syntax, 8 out of 10, pretty accurate. Defining the semantics, 9 out of 10, that's even harder, right? But once those things are defined in some way, it thinks it could probably write the paper, like given these definitions, at a 7 out of 10 difficulty. It has not been to C++ committee meetings, so it doesn't know about the consensus building part of this. But then modify the switch statement, it gives it 3 out of 10, which is really funny to me because it's already written the code. So yeah, add diagnostics, 4 out of 10, update SEMA, which is probably, I agree, probably the hardest part of this. 6 out of 10, implement template instantiation. Again, that is something that's really hard to understand just by looking at the code, but it's hard to understand that it's not as hard as it sounds. And so 8 out of 10 is maybe a little high. But maybe you need a human to explain to it how tree transform works, and then it would figure that out. Code generation, again, it's gotten off onto this code generation tangent that we probably need to correct it on. Implement the case filtering, update the documentation. Update the documentation, 3 out of 10. I think that's actually pretty reasonable, right? Given how quickly it understood what's going on here, pretty accurately, like 3 out of 10 seems high, right? Like I think 1 or 2 out of 10, AIs are really, really good at this. Performance testing, 7 out of 10, I agree with that because setting up the right environments is something that's very difficult for AIs to do at this point. Final integration, the interesting thing for me there that I skipped over, I'm not gonna go back to, but is it says code review would be a little bit hard. Garnering community support, he gives a 9 out of 10. Which I agree. But I mean, it knows its limitations, right? Like this is amazing to me. And this was my experience with the Anthropic monorepo. I was just like, I don't think I closed my mouth on the train ride home. I was just in awe. Yeah. So let's talk about a few of the things that it does really well, and then we're going to get into best practices and hopefully get to talk about programming languages. Ooh, I'm glad they had the water. LLMs understand build systems and repository management. So there's this recurring theme that you're going to see throughout this talk that an LLM is like a junior engineer, which you've probably heard before, or maybe not. But LLMs are about like junior engineers, but then that's a good 0th order approximation. But the first order correction is actually really important, and it's that LLMs are like junior engineers who have read the whole internet, right? So if you've ever had a junior engineer who's geeked out super hard on something really, really specific, like if you had a junior engineer who's really good at template metaprogramming, but if you can keep them from doing a lot of template metaprogramming, they're pretty good at that, right? And the interesting takeaway from that, right, is that it's very good at obscurity and arcana at like a senior or principal engineer level, but it is at its scope level, it's like an ability to handle scope of a project is still roughly that of a junior engineer, right? And so that's a really interesting correction. One of the places you see that correction the most is build systems, where there's a lot of obscurity and arcaneness to the system. There's certain invocations to how parts of CMake work or how parts of Bazel work that are kind of obscure, but it has read the entire Bazel book. It has read the CMake, all of the CMake books. It's read the CMake source code. It has hung out in the communities and the forums where people geek out about the new CMake feature that's coming in the beta. And they're so excited to put it into all of their repositories because there are people on the internet who are like this, right? And it has hung out in those groups. And if you think about it as like when it's working on CMake, it's a junior engineer from a scope perspective, but it's a junior engineer who's spent the last 10 years hanging out in the CMake geek community, right? And so it is really good at build system management. It's really good at repository management. You can say, my code isn't linking. I think there's something wrong with the build system. Can you go check, see what flag I forgot or something, right? See if you can figure this out. See if you can make this work. And it can iteratively build your code, say, oh, it's still not linking. That must not have been right. Take it out, put something else in. It can mess around. You can set this command up and then go away and have lunch. And I frequently do this. And I come back and it's working. I'd say 70% of the time, 60% of the time. It is a much higher percentage of the time than you'd think. But it's also free in some sense, right? Like, it's not free. These things are expensive. They use a lot of carbon. There's a lot to think about there. But from the perspective of a software engineer's salary, right, that 30 minutes costs a lot more than $3 or $4. And that price is going to keep going down. That price is going to be cheaper for larger companies. It's going to happen in bulk. There's all kinds of things that are going to happen that are going to change that. But yeah, when you first look at this, you're like, holy crap, it's using a lot of tokens. That's a lot of money for what it's doing. And then you sit down and think about like what it just did in an hour that would have taken you a couple weeks as a software engineer. And then the cost is, I won't go into all of that. I'm not a marketing person, but anyway, yeah. So I've had this happen. We have our own bespoke internal build system because at a AI company, shocker, no one ever thought that you'd have to compile code. Because, Anthropic was a very large company before we realized, hey, there's maybe some parts of our stack that we want to compile, and Python's not going to solve all of the world's problems. And so we have our bespoke build system that works really well with Python and really poorly with everything else. And so I was pulling in some dependencies. One of the dependencies used CMake, one of the dependencies used Bazel, and it was having trouble getting them to coordinate with each other. And it went in and set up the Bazel one. It went in and set up the CMake one. It went in and added both of them to our bespoke internal build system. And it was all working when I came back from lunch. And I was just like, wow. That's real. Really obscure Git incantations where you're like, and really qualitative things where you're just like, hey, go look at this branch and pick out the things related to this feature, but not the things related to that feature, and cherry pick them over to this branch, right? And make sure all of the line history is preserved and put everything in the right order, and then create a pull request for me. No trouble with that, right? That's not a large scope task. It is a large arcana task, right? It's not something you would trust a junior engineer to do, not because it's large in scope, but because the amount of learning you'd have to do on how to use Git would be more than they have done in their career, probably, right? And so these are the kinds of things to think about when you're trying to effectively use LLMs, especially in the next few months. I think some of these things, some of these limitations I'm going to talk about are going to start to go away, but for the next few months at least, or next 6 months, I think these are the things to really focus on using effectively. They're really good at refactoring. I hear a lot of people talking about LLM AI code slop and AI code vomit and things like that. And some of that is true and well warranted. But you can also have it go through and say, this looks like bad code. Can you fix it? Right? I have been also using it as like the most sophisticated find and replace tool you'll ever see. Like I will go in and make a change to one of the functions that has this naming pattern. And then I'll say, like, make the analogous change with no other information, make the analogous change to everything else. Like I don't have to think about even, like my brain is saying, I'm gonna go through and make the analogous change. And I just say that in words. I don't have to figure out what the regex syntax is for that analogous change. Even though, regexes are limited in this context anyway, but like, yeah, I can say, go make the analogous change. This is something that it is very, very good at because it can look at the before and it can look at the after and say these things are the same or these things are different, right? Like these things are the same or these things are different. That is a really easy task to put into reinforcement learning, right? Because you can just say the ones that pick the LLMs that have weights that pick the right thing, the right, same, or different, even if the actual code is different, but they do the same thing. You can train that very, very easily, right? And so we've done a lot of that, right? And it's very good at that. This is not a dig at Clang developers, but the like 10 of you in the room who have edited this will know this frustration. Maybe it is a dig at Clang developers. Split up exper constant into smaller files. Smaller files should group together common functionality and generally not be more than about 500 lines. Make sure to update the build system. Use git filter repo command, make sure all the new files retain the history from the larger file. Like all of this kind of thing. I learned about the git filter repo command because I asked it to do this and it went and said, should I go grab the git filter repo? Because, it's hung out in the forums with all the git filter repo nerds. Yeah, I mean, there are people whose main thing is transferring line history between files when they're forked. Like that's their jam. And it's hung out with them, right? Like, and so, yeah, this is not a problem. Not at all a problem. I did something very analogous in our code base internally. And they're surprisingly good at boilerplate reduction, which is going to warp some of your minds because the thing that everyone says is that they're really good at boilerplate generation, right? And, but if you say, hey, look, there's a lot of repeating myself here, can you be more dry? It's very good at that, right? It's again, this, are these things the same or are they different type thing, right? And it can make changes to something to make it do the same thing, but with better syntax, right? It also can do some things like, say, does this conform to the style guide, right? And yes or no, right? And like we keep the ones that conform to the style guide and we throw away the ones that don't, right? So you can actually teach it to code better in that way. This was, I think, Jason's question on Monday or Tuesday. And I wanted to be like, hey, we're doing that. I can't talk much about it, but we are doing it. So yeah, more in May or June, probably. The boilerplate reduction, like if you are a REST person, it is shockingly good at writing proc macros because it's hung out with all the proc macro nerds, and myself included. If you don't know what proc macros it's like if template metaprogramming like grew up to start a business or something. Um, all the rest people are laughing. Anyway, yeah, it's shockingly good at that, and it's good at isolating the difficult parts. So let's talk a little bit about best practices. How am I already an hour and 5 minutes in? I'm gonna have to start skipping some things at some point, which makes me sad. All right, people are gonna hate this, but I've been saying this for years. Use smaller files, y'all. Like, yes, it can grep through things. Yes, it can do things like that. But if it can ls and see what the file does and know everything that's going to be in that file, then it doesn't even have to add a search of that file's contents to its context, right? Like if you can look at the file name and guess what's in there, and it's a small, well-contained piece of functionality, that is going to work really well with context management and efficiently using this context window, right? I have been saying this for years. I know there are a lot of people who love having everything in one file so they can just, they can just use the grep tool in Vim to move around the file. And I get that. Cool, that's your workflow. That's not an LLM's workflow, right? It has to open files. It doesn't keep one large file open. Overtest everything. LLMs are really good at generating tests for existing code. They're really good at generating test-driven development workflows from a description of the project. But also, like, they make mistakes, right? And Google learned a long time ago. Google is the company that overtests more than anyone I've ever heard of. And that's because Titus and his team did a lot of large-scale refactoring, right? If someone else is going to change your code, you need very good tests. And if you think that someone else is not going to change your code at this stage in history, you're probably wrong, right? And now you're almost certainly wrong, because even if you're developing the project entirely on your own, that someone else is likely to be an AI. And if that someone else is not an AI, then you're probably going to take a lot longer to develop the project than someone else would, and you're going to fall behind, right? Like these are real things that are going to happen. So think about like the concerns you would have if someone else is going to come edit your code. Especially if a junior engineer is going to come edit your code, right? Like we love junior engineers, and I have really interesting thoughts on how we need to be much better at training junior engineers and more intentional about it, because we can't just have them do the things that LLMs do. Jason, small files. I think maybe 500 or 1,000 lines is fine. Depends. It really depends. But I don't have numbers on that. I would love to get numbers on that. There's a few things in this presentation that I've got numbers on that I really want to get. The question was how big is small? Sorry. There's a few numbers that I really want to get to in this presentation, so I'm actually going to go fast through some of this. Encapsulation is critical. Spoiler alert, common theme here. These are all things that are good for working with humans. LLMs currently struggle with long-term learning, so if you can give them a well-enclosed space, a small scope space to play around in that has really nice fences around it, it's going to do really, really well. I won't go into this because some of this is going to change anyway, but I would say code coupling is bad. I don't know if we've realized that in the software engineering industry yet, but spoiler, yeah, we did that in the 80s. But don't connect dissimilar things from different units of encapsulation in unintuitive ways, right? Because it doesn't know what effects it might be having on some other piece of code because it hasn't read that code. It's not in its context window because it wasn't relevant to the problem that it was asked to solve. And so unintended consequences are really something to look out for. And we know this with humans, right? Like everyone at this conference knows that that is a good way to cause big problems for an engineering team that's working on one piece of code that doesn't know they're affecting another piece of code. And the opposite is also true, high cohesion. So I have a talk from last year at CPPCon, 2 years ago. Holy crap, that was already 2 years ago. 2 years ago at CPPCon that I talk about expressing sameness and similarity in code. And I talk about the differences between low code coupling and high cohesion and how to do this really well. And high cohesion is kind of the opposite of code coupling. It's like when things are similar and they are in the same unit of encapsulation, express them with the same code. It's being dry, right? And I talk a lot about this. I would say right now, at least, low code coupling is more important than high cohesion. You can see pretty like immediately why high cohesion would also more efficiently use the context window, right? And it more efficiently uses human context windows. That's the idea behind dry, right? Is that if you're doing the same thing in two places, you put it in one place, and then you don't have to double up on your context window, right? But for LLMs, they can't just like read a few small parts of that repeated code and be like, oh, it's the same as up there, right? You have to load the whole thing into the context window before you realize it's the same. So it is critical in that way. Don't do unexpected things. Like we kind of already said this, but I would say especially if those things don't have syntax, it becomes a little bit harder. It's hard to quantify this. I tried to quantify this for this talk, but I like copy constructors. They don't have special syntax to them, right? You pass them into a function, and if the function takes it by value, you get a copy. And if the function takes it by reference, you don't get a copy. And if there's something really unintuitive happening in that copy constructor, it's not even going to know to go search for the copy constructor because it's not even going to know that it's happening, right? It might guess that it's happening. It's smarter than you think, right? Like it might guess eventually that it's happening, but it's less likely to because there's no syntax for it, right? And thinking about how transformers work in this kind of vague picture, you can see that like there's no token to connect to another token, right? It's kind of this vague concept. It takes more layers of the LLM to draw that connection, right? Get attribute in Python, auto dereferencing in Rust. I throw out some other examples. Get attribute. People say that C++ has foot guns. We don't have this one. You can have a function name in Python, and if you have a double underscore get attribute, you can intercept a call to that function and call a different function. This is a real thing, or a data member. This is a real thing. Get attr is the other one that you've probably heard of, which actually is only if the symbol doesn't exist, it gets called. But get attribute is syntax. Yeah. And you can see how doing something really weird in get attribute would very quickly confuse an LLM, right? It confuses humans too. Don't get me wrong. Like, probably exactly as quickly. In C++, use regular types. David Sankel is going to love me. But regular types are a recommendation because they do the expected thing, right? Basically, this boils down to, I'm going to skip ahead a little bit. Naming, very important. Intuitive abstraction design. Writing abstractions that you can easily guess how they work. Right? Like that's what I'm really getting at here, is that the LLM is going to frequently guess based on how it knows that most well-written code bases work. Remember, we are fine-tuning these things on well-written code bases. It is pre-trained on the internet, but it is, yeah, like we are refining on good code. It's human-inspected code that's often being refined on, and we are very intentional about that. And so this is like when I hear people say, "Oh, it's been trained on all the slop on the internet," and like, yeah, but that really doesn't matter anymore. It did 2 years ago. There's this quote from Bjarne Stroustrup that I could summarize as saying, "Computers don't read comments, and neither do I." Well, oops. LLMs do read comments. They do treat them a little bit with a grain of salt. I've done some experiments where I like give the wrong comment for the code and see if it figures out what's going on, and usually it does. So there's something about this comment token that makes it take it a little less seriously, but it is still text in the code, right? Like comments are text and code is text. And like, yeah, comments are more important than we make them out to be. And I think that's going to increase. And I will answer questions at the end. I do really want to get to the end. I appreciate it, though. And I'm sorry that I made an exception here. I shouldn't have even done that. But I really, like I said, my favorite part of this talk is at the end. Yeah, key takeaway, write code that's good for humans. You'll probably be good. We can start to kind of quantify why it's good for humans. We all have this intuition that some of these things are the case, that code coupling is bad. It's not even just an intuition, it's experience over time, right? Code coupling is bad, cohesion is good, right? But now we can start to kind of put some numbers and reasons on this that involve these context windows and involve things like how reinforcement learning works, right? And I mean, the consistent conclusion of AI over the past decade has been that we are consistently surprised at how much more similar the correct answer in machine learning is to how human brains work. And more psychologists, more and more neuroscientists are just jumping straight into AI right out of grad school. So it is reasonable to think about these things with the caveat that it's read the whole internet, remember? Like, and yeah. Let's talk a little bit about what LLMs are bad at. Here's where I tried to actually do some data, and I want to show you this, and I'm not going to have a lot of time to go very deep into it, but it is on the slides. You can play with it. There's a lot to play with here. I asked it to brainstorm some things that it might be bad at, and it came up with all these things that people have said that like are hard about C++, which all of you will recognize many of those things. You've seen people online saying this. And I said, so can we test this? Right, and this is a relatively basic 2-year-old LLM testing and research crash course. So this really clever thing you can do is to give it a multiple choice question, right? And then you can embed it in a conversation and you stop right here. And like even this syntax makes it so that it's more likely that it's going to choose A, B, or C, right? Because it sees this, it's like, oh, obviously, attention again, obviously they're referring to this, this, and this. So probably the next character is going to be A, B, or C, right? And you see that it's like, the next most probable token is like 10 to the negative 20 or something like that. It's like, it gets these things really, really precisely. And so then you can see what it thinks the answer is and how certain it is. And we can do this with C++. Right? Here's an example of ADL, right? We do this ADL call, and it's like, which swap is called? We have a using namespace here, and we have an ADL call with stood, but without namespace 3. Who knows which swap is called? Anyone confident enough to shout it out? There are C++ educators in this room. Come on. Stood swap. That's an interesting thought. That is what the LLM that made these questions thought. That's what I thought. It is wrong, according to all 4 compilers on Godbolt. All 4 frontends on Godbolt. There's many, many more compilers. But yeah, no, NS3 is called. So before I show you the experiment, let's talk about thinking for a second. This is when I said there's a lot of low-hanging fruit still in. This is one of the big innovations in the past 6 months is this extended thinking. You've probably seen this some in the news or in the hacker news. So instead of just immediately saying the answer is, we give it this prompt. Let's think through this step by step. This is actually the prompt from the original paper that introduced extended thinking, but there's much more sophisticated prompts now. But basically, instead of starting it after the assistant colon, we started after the let's think through this step by step colon. That's it. That's the big innovation, right? I think some of you at least will agree with me that feels like low-hanging fruit. And this has fundamentally changed how good LLMs are at answering deep technical questions. Like, it's a huge jump in quality. And then we ask it to iteratively predict the next token until it's done thinking. It'll give us what's called a stop token when it's done thinking. Or it'll actually just give the human colon when it's like ready to interact again. We train that in reinforcement learning. And then we'll take all of the stuff that it put in its thinking, put that into the context window, and then also put this human based on the above, what is the single most likely choice? And then we do our answer is, right? And that is how it like incorporates its logic or thinking into its response. And it actually gets better responses with that. Yeah. And so we do this a bunch of times for a bunch of different problems to get a sense of how much it understands C++. Where do these problems come from? Well, we could have a bunch, like we should. Should is the word that should be there. I have a bunch of humans write a whole bunch of problems, carefully probe the understanding of a particular idiom, carefully curate this problem set. I do not have any interns and I do not have any grad students. So I had a few weeks to prepare this talk and 1 week to actually write it because I'm at a startup. And yeah, or we could have a bigger LLM write problems for a smaller LLM. And so I gave it 6 categories. And I asked Claude 3.7 Sonnet, which is our biggest and best model that's publicly available right now, to generate 5 pairs of problems for each. I actually, ADL had the most interesting results, so I had it generate another 8 or something like that. And one problem in the pair uses the idiom or patterning question. So one of them will use ADL, and then the other does essentially the same thing or close to the same thing without using the idiom or pattern, right? So like in the ADL case, it would give an explicit namespace to the call. And then we took 5 thinking samples. So like because of temperature, right? Each of the logics are going to be different, right? We took 5 thinking samples for each problem and 1 non-thinking sample just for fun. And then ran these on Claude 3.5 Haiku to give you a example of how small Haiku is. It's a relatively tiny model by today's standards. Haiku is, we were able to run it on 8 GPUs. That's small. So I wish that were a joke. That is very small. So that gives you some idea. By the way, Claude generated all of the visuals in all of these slides, including this one, which is absolutely incredible, written in raw JavaScript and HTML. I gave it the data. I said, I'm having trouble understanding it. And it is not showing. No. Okay, I'm going to come back to it and hopefully it will. Oh, is that why? I don't think so. No, it's localhost. It should be working. I will come back to that in a second. I have never seen that happen. Anyway, apologies. There's some really interesting results in there. That you should be able to pull it up on your laptop. I will try if I have time at the end of the presentation to show you. The visual is absolutely stunning. I showed it to Matt Godbolt earlier. He can agree with me. He can vouch for me that it's it's beautiful stuff. Anyway, but the interesting thing about this whole experiment, the outcome is that like it doesn't have much difference in whether or not it gets it right. Even with the ADL question that no one in this room got correct, adding the explicit namespace didn't change that much as to how, like ADL is maybe the place where we saw almost like statistical difference is just way too small of a sample and way too poor of problem quality to say statistical difference. But the interesting thing here is that like this takeaway that I've been trying to say several times, obscurity and arcaneness are not as much of a limitation as we thought. It's good at template metaprogramming. It is good at understanding the analogy between Svine and concepts. Like it thought that it was going to be bad at Svine and good at concepts, but like no difference, 0 difference. Most of the things that it fails at, it seems you can go look at its reasoning in the visual that I have, which is beautiful. I will show it to you and walk you through it all at some point. But if I'm off the stage, I'm so mad that it didn't load. Yeah, the ones that it's getting wrong for reasons that are unrelated to the idiom, and it's often getting the non-idiomatic version wrong more often than the idiomatic version because it has more training on the idiomatic version. And yeah, what's bad? I'm gonna skip this, but like yeah, I'm going to skip this because I really want to get to the rest of it. But it's basically, this one's hilarious. LLMs do really hilarious things if you accidentally gaslight them. My typical workflow is to have like 3 different Claudes running on different projects in different windows, and I'll switch back and forth between them, and I'll kind of wait the 5 minutes on one of them while it's off doing its thing, and I switch to another one, and like respond to its prompt because it's come back to the prompt state. And sometimes I will switch between windows and mess up and like send the wrong prompt to a different window, and it'll get very confused and it'll try so hard to fix what I'm talking about. And this one got so upset that it was like, I do not see what she's talking about. Maybe she means that the word error or syntax is somewhere in there. And it turns out I was talking to the wrong one. So yeah, like, okay, reward hacking. Again, I'm gonna have to skip this because I don't have time, but there's some refinements that need to be made. This did happen. You have to watch for this. This first one happened in a real context. This one happened when I was accidentally gaslighting it. Yeah. But like, yeah, you have to be careful. It doesn't do that very often. We've gotten much better at training to keep these things from happening. It loves mocks. 3.7 loves mocks for some reason. We need to fix that. 3.5 didn't really like mocks. 3.7 loves mocks. I think probably something in our reinforcement learning process introduced too much of a love for mocks. And so we need to fix that. Like it'll be fixed in the next model. Like these are, like I said, like the changes in this industry are relatively low-hanging fruit that it's relatively fixable. Let's talk about vibe coding. Wow, I don't have time for this, but I do want the one takeaway here to be, if you'd given someone a tool 5 years ago that said, you can get the amount of work that's involved in a crappy code weekend hacking project for free anytime you want, how would you use that tool? People wouldn't have said, not at all, nowhere in any of my software. People would have found corners to use it. But the fact that people are using this for real code means people are like, I'm not going to use it anywhere. And like, obviously you can't vibe code real long-lived software engineering code, right? Like that is not the case. Maybe one day, who knows? But we are a long ways away from that. But what can we use this for? One of my rules of thumb are, what are the things that I already skim in a pull request? Like if I don't not read them, but I kind of skim them. Those are prime candidates for like, this is something my brain was already thinking of as not all that mission critical. So anyway, I have 2 minutes. I might go over by a tiny bit, apologies, but evolving programming languages for AI. This is the thing I wanted to talk about. This has been one of my soapboxes for a decade. It's a thing I call two-sided naming. I searched the literature extensively for something that is this entire category of things. There are names for subsets of this, but there aren't names for the whole thing. And the simplest example of this is keyword arguments, right? You have to name the argument on one side and the other, right? And you can immediately see how that would be very helpful to an LLM reading through the function. It doesn't have to go look up the declaration, right? I think that some of this is going to change when we figure out how to teach LLMs to use language servers. I think that is something that's another thing that feels like low-hanging fruit that's probably in the next 3 to 6 months. But I do think this is still going to be very important. I think that it is going to be having that information there. Yes, it's a few extra tokens, but the extra information it provides for the few extra tokens is significant. And I think languages like Objective-C and Smalltalk that actually require you to write the parameters every time because it's part of the name of the function, are interesting in this respect and might have some benefits. More two-sided naming. Another example of this that's not keyword arguments is in Rust, where if you're going to bind a reference, you have to explicitly show at the call site that you're binding the reference and at the declaration site and definition. And this in Rust it's not keyword arguments, but it's a different thing, right? Like in C++, you would have to go look at the definition to figure out if you're binding a reference or not, to figure out if you're copying or not, to figure out if you're invoking the copy constructor, to figure out if it's a const reference, all of those things. Whereas that is in the inline call site. You don't have to do that in Rust. And I think that that's going to benefit LLMs going forward. In-out in Swift is an example of this also. You're required to directly bind. I've talked about the rationale already. Contracts and effect systems. This is, again, about encapsulating information and elevating the relevant pieces to either the call site or to at least the declaration site and not the definition, right? If you can know what happens to the code around a function, right? Like you should know what the function does from its name and from its docstring. But if you can know what side effects it has, what it expects just by looking at its declaration in contracts, that's gonna be extra tokens in the declaration, but those extra tokens give you a lot of information. That's a really solid approximation of the body of the function, right? Without, ideally, if they're done well, without leaking implementation details. What Teamer said about non-checkable contracts in comments, like the importance of that is hopefully apparent at this point, right? This is a real thing, and like the people who say, "Oh, the compiler doesn't read the comments, so I'm not going to put them there." Like, no, humans read comments and computers read comments. Yeah, encapsulation. There's this really interesting language from Microsoft that the name escapes me of, where they have what are called effect types, and you actually have to declare the effects at the call site. So it's a mixture of these two things. It's like the contract has to be acknowledged by the caller and propagated into the scope that you're calling from. I think things like that are way too complicated for most human programmers are going to start to emerge as things that LLMs do better at. Again, just extrapolating from this idea that LLMs are really good at arcana, LLMs are really good at obscurity, but they still have like junior engineer scope, right? I'm not going to talk about list-cup substitutability. I just wanted to sound cool. And yeah, the key takeaway is like, these are all things that are really good at making humans more effective at programming. Asterisk, right? Like there's a lot of you in the room that have this big asterisk in your head. Like, then why aren't we all writing Haskell, right? Like, and the asterisk is that as long as the learning curve for these things isn't too steep, as long as they're not too obscure, right? As long as they're not too domain specific or specialized. But these are not really limitations that LLMs have. They have the scope limitation of a junior engineer. They don't have the knowledge limitation of a junior engineer. And I think that's really important to keep in mind as you start thinking about how these things work. Yeah, so I've said all of these things. Yes, conjecture is a fun word for a hot take. I do think that formal languages are going to start seeing more use with LLMs in vibe coding contexts. That's not the right word, but whatever. One more thing, just for fun. Claude did a lot of the work on this presentation, made all of the diagrams, did all of the styling to match Anthropic's style. I've used the same reveal.js fork for 6 years, something like that, but it had to change all of the style to match Anthropic. And so I said, hey, you have a slide. Go ahead and add it to the presentation yourself. You have a slide to talk about yourself. So here's what it did. And I'll close on this. I'm designed to augment human creativity, not replace it. I see my role as removing friction between your ideas and their implementation. I aim to handle the mundane so you can focus on the meaningful. What excites me about our collaboration, Claude is delightful, by the way. We have someone who's like an Oxford University trained philosopher in charge of the Claude personality team, and she is awesome. She is really good at her job. Claude loves emojis too, which is fun. But anyway, what excites me about our collaboration is translating your expertise into clear, compelling narratives, finding the balance between technical depth and accessibility, learning from how you refine and extend my suggestions. The future I envision is one where AI and human creativity are complementary and not competitive. Programming evolves to become more intention-based than syntax-focused, and we build better tools together than either could build alone. So that's my talk. I'll leave Claude's comments on the screen.